When a spaceship explodes in a science fiction movie, you expect a roaring boom, but physics dictates a much quieter reality: absolute silence. We learn the reason for this early in school. Sound requires a physical medium to travel through. Over 2,000 years ago, Aristotle correctly observed that sound is simply the propagation of air pressure variations. Bodies strike the air is contracted and expanded, and that motion carries forward from one pocket of air to the next. Outer space is a vacuum, almost entirely devoid of matter. Without a dense atmosphere of molecules to contract and expand, there is nothing to carry a pressure wave. This absolute rule of a silent universe has stood as unquestioned common knowledge for decades. The idea of hearing a sound in the cosmic void seemed physically impossible. Then, astrophysicists looking deep into the cosmos found a clear contradiction to that rule. Researchers analyzing data from the Chandra X-ray Observatory detected a measurable acoustic signature emanating from a supermassive black hole at the center of the Perseus galaxy cluster. They had found physical acoustic waves rippling through a region of space typically defined by its total absence of matter. To resolve this apparent paradox, we have to abandon our human-scale perspective and zoom deep into the microscopic mechanics of empty space. We need to look closely at the mechanics of how energy moves. Light and sound travel through an empty void in entirely different ways. An electromagnetic wave, like starlight, behaves like a marble thrown across a room. It consists of self-sustaining, oscillating electric and magnetic fields. It relies only on its own momentum and requires no physical medium to reach the other side. A mechanical wave, like sound, operates like a line of falling dominoes. Its energy relies entirely on one physical particle colliding with the next to transfer its momentum. A vacuum doesn't kill sound by actively blocking it. It simply removes the dominoes needed to carry the signal forward. Physicists measure this with the mean free path, the exact average distance a particle travels before colliding. At sea level, a nitrogen molecule travels just 68 nanometers before striking a neighbor. But in the diffuse interplanetary medium, a particle travels 150 million kilometers before making a single collision. When attempting to broadcast a human audible sound in this environment, the wavelength is simply too short. The acoustic energy falls into the massive gaps between particles and instantly suffers viscous damping, dissipating rapidly into heat. Space isn't a true void. Its dominoes are simply spaced far too far apart for human-sized sound waves to knock them over. On a cosmic scale, the regions between galaxies contain a highly diffuse, incredibly hot plasma known as the intercluster medium. The Perseus galaxy cluster provides a perfect example of this plasma-filled cosmic environment. This image shows a simulation of propagating sound waves. In Perseus, extreme energy from the active galactic nucleus compresses the diffuse plasma into physical ripples. To propagate without dissipating, the pressure wave's physical wavelength must be larger than the plasma's mean free path. Because the waves generated by the black hole are so immense, they successfully cross the vast distances between particles. Actual physical pressure waves are continuously propagating across hundreds of thousands of light years. The acoustic wave echoing through the Perseus cluster vibrates at a very specific pitch, a B-flat. However, its massive wavelength registers 57 octaves below middle C on a standard piano. This frequency is millions of times deeper than the absolute limit of human hearing. The universe is not silent. It is booming with physical acoustic energy. We are simply too small to hear the cosmos speaking.